non-aqueous solvent. Most of the chemical reactions are carried out in the solution, and the behavior of substance also depends upon the nature of the solvent. In the earlier days of the development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability and ease of purification, together with its favorable physical and chemical properties, such as long liquid range with the high electric dielectric constant, specific heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic, and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying and chemical reactions are called non-aqueous solvents. Attempts have been made to find some other substance which could behave as a good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether for dissolving organic compounds which are insoluble in water. Now, there are many other solvents available, for example, liquid NH3H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In present unit, we shall discuss briefly the important features of non-aqueous solvents such as NH3 and SO2. Physical properties of solvents and their role in chemical reactions. The usefulness of a solvent is determined from its specific properties that may help to carry out the chemical reactions and separate the products more conveniently. Some of the important physical properties of the solvents are discussed below. The melting point and the boiling point liquid range. The melting point and boiling point of a solvent determine the temperature range within which the solvent can exist in liquid state under atmospheric pressure. Since most of the reactions in a solvent system are carried out in liquid phase, the melting and boiling point give the temperature range within the solvent is useful. A melting and boiling point for some common solvents are given. It is clear from the above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperature, while NH3 and SO2 can act as solvent only at low temperature. Heat of fusion and heat of vaporization. The value of heat of fusion and vaporization help to know the nature and strength of the forces which hold the molecule of the solvent together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or vaporization, stronger are the intermolecular binding force in the solid or the liquid respectively. Therefore, the magnitude of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Troughton constant. Delta H evaporation by Tb is equal to Troughton constant. For normal liquids, if the molar heat of vaporization expressed in calories and boiling point in absolute scale, then the Troughton constant has the value 21.5 are in joules. Troughton constant is about 90 for normal liquids. Such liquids exist as independent molecules without any bonds between them. A higher value of Troughton constant indicates associated molecules. For example, common solvent like water, ammonia, hydrogen fluoride have Troughton constant value greater than 21.5 and are therefore associated liquid. A molecule of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged ends of the molecules come near to each other. The molar heat of fusion and vaporization of some solvents are given in the table 2. The inspection of table 2 showed that the values of molar heats of fusion for water and ammonia are almost same. This means that the forces which hold the molecule together in water and ammonia are of same magnitude. Dielectric constant. This property is a measure of polar nature of the solvent and helps to estimate the solubility of a polar or non-polar substance in the solvent. According to the Coulombic law, the force of attraction between two charged ions is given by F is equal to Q plus Q minus by E R square, where Q plus and Q minus are the charges of the cation respectively. R is the distance between them. E is the constant called the dielectric constant of the solvent. If E is large, the force will be small. As a result, only a small amount of energy will be required to separate the ions, and hence it will be easy to dissolve an ionic substance. Thus, in solvent of high dielectric constant, the ionic substance will dissolve readily. With a decrease in dielectric constant, the solubility of the ionic substance will decrease. The dielectric constant of some common solvent are given in table 3. It is clear that the solvents like HF and H2 are good solvent for ionic and polar compound because of their high dielectric constant value. On the other hand, solvents like NH3 and SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compound, and especially those containing multi-charged ions. For example, carbonates, sulfates, phosphates are practically insoluble in liquid ammonia or liquid sulfur dioxide. Dipole moment. Dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large electric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, large is its dipole moment. Solvents have high dipole moment, having greater tendency to dissolve the polar or ionic substance. This is because the fact that the greater polarity results in a strong bond between the solvent and the solute molecules, and large solvation energy is released. This helps solvation energy is sufficient to overcome the lattice energy in the solute molecule and helps in dissolving the solute. Viscosity. It is a measure of fluidity of the solvent. Solvent like water, ethyl alcohol, carbon tetrachloride have low viscosities and high fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rates at ordinary conditions. In solvents of low viscosities, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increasing the viscosity of a liquid increases the difficulty of such operations. Types of solvent. Non-aqueous solvent can be classified in many ways. The following are the important classification based upon the chemical properties of the solvent: protonic and non-protonic solvent, acidic, basic or amphiprotic solvent, coordinating and non-coordinating solvent. Protonic and non-protonic solvent. Solvents from which protons can be derived are called protonic or protic solvent. Therefore, protonic solvent contain ionizable hydrogen. Common examples are H2, HF, H2SO, or HCN. The solvent from which protons cannot be ordinarily derived are called non-protonic solvent. These are also called aprotic solvent. In other words, these solvents do not contain ionizable hydrogen atom. Common example as liquid SO2 and 2O4, C6H6, CHCl3, CCl4. Acidic, basic or amphiprotic solvent. This classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate protons are acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride, acetic acid, etc. Solvents which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridine, hydrazine, ethylenediamine. Solvents which neither have a strong tendency to gain nor a strong tendency to lose proton are called amphiprotic or amphoteric. In other words, they neither behave as a strong acidic nor basic, but can behave as acidic as well as basic depending upon the nature of reacting species. For example, water, ethyl alcohol, methyl alcohol. Ionizing and non-ionizing solvent. The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some examples are H2O, NH3, HF, SO2, N2O4, ClF3, BrF3, PoCl3, etc. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are called non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbon. These are non-polar or non-ionic in nature. Coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvent. For example, NH3, SO2, dimethyl sulfoxide, acetonitrile, dimethyl formaldehyde, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metals are of ions of the solute are called non-coordinating solvent. For example, CCl4, saturated hydrocarbon, etc. These are not of much interest to inorganic chemists. Types of reaction in non-aqueous solvent. The following types of reaction commonly occur in non-aqueous solvent. Metathetical or precipitation reaction. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reaction. These types of reactions can be predicted if the values of solubility of products of the compound formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. 2AgNO3 plus BaCl2 gives 2AgCl plus BaNO3 whole twice 2. On the other hand, in liquid ammonia, a precipitate of silver chloride combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in the solution. 2AgCl plus BaNO3 whole twice 2 in liquid NH3 give BaCl2 plus 2AgNO3. Therefore, reversal of the chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic salt. The salt formation. The reactions between appropriate acidic and basic substance to form salts are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium urate cannot be prepared by the reaction of urea and sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water and urea ion. It will take a proton from the water to form hydroxide ion. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. Urea plus sodamide gives sodium urate plus NH3. Acid-base reaction. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept. An acid is a substance that by direct dissociation or reaction in solvent gets the cation, and a base is a substance that gives the anion characteristics of the solvent. The acid-base behavior of a substance depends on acid-base nature of the solvent, character of solute-solvent interaction. In the case of protonic solvents, cation is solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive act as acid and NH2 negative ion act as base. The neutralization reaction is acid, base, liquid NH3, salt plus solvent. In non-protonic solvents such as benzene, carbon, CCl4, Lewis acid base type of reaction can occur because of the non-ionization of solvent. The acid-base behavior of a solute in solvent depends upon the acidity or basicity of the solvent. For example, acetic acid behaves as a strong acid in ammonia and weak acid in water, but a base in sulfuric acid. Solvolytic reactions or solvolysis. The reaction in which the solvent molecules react with the solute in such a way that the solvent molecules split up into the two parts. One or both of which get attached to the solute molecules and ion are called solvolytic reactions. Since these reactions occur through self-ionization of the solvent, the concentration of either cation or the anion is changed. For example, the solvolytic reaction in water, ammonia, and ethanol are given below. Water is solvent. 2H2O gives H3O positive plus OH negative. Autoionization. SO2Cl2 plus 4H2O gives SO2OH whole twice 2 plus 2H3O positive plus 2Cl negative. Concentration of H3O positive is increased. Ammonia as a solvent. 2NH3 gives NH4 positive plus NH2 negative. H negative plus NH3, NH2 negative plus H2. Concentration of NH2 negative is increased. Alcohol as a solvent. 2C2H5OH gives C2H5OH2 positive plus OC2H5 negative. Autoionization. CH3 plus C2H5OH, OC2H5 negative plus CH4. Concentration of OC2H5 negative is increased. It may be noted in the case of solvent like water, ammonia, alcohol, acetic acid. The terms hydrolysis, ammonolysis, alcoholysis, acetylysis are used respectively. Solvation. The reaction in which molecules of the solvent get attached to a solute species are called solvation reaction. The species formed is called solvate. The solvation reactions in water, ammonia, alcohol are called hydration, ammoniation, alcoholation, and the resulting solvents are called hydrates, ammoniates, alcoholates. CuSO4 plus 4NH3 gives ammoniate, CSO4.4 NH3, BSO4 plus 3H2SO4 gives BSO4 3H2SO4, solvate of sulfuric acid. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis because in many solvolytic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecules remain in the resulting product. Liquid ammonia is one of the most extensively studied non-aqueous solvent. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble to those of water. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following point. Liquid range. The melting and boiling points of liquid ammonia are lower than those of water. In liquid ammonia, the liquid range is from -77 to -3 degrees Celsius, and therefore it represents many handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen. However, NH bond is weaker than OHO bond. As a result, the freezing point and the boiling point of ammonia are less. Since ammonia is less associated than water, it is better solvent for organic compounds. Dielectric constant. The dielectric constant of ammonia is 22 at minus 33.5 degrees Celsius, lower as compared to water, suggesting its lesser tendency to dissolve any compound. Liquid ammonia, therefore, a poor solvent for any substance. Soluble salts include most ammonium salts, nitrates, thiocyanates, and iodides. Self-ionization. Both ammonia and water show comparable ionization as represented 2NH3, NH4 positive, NH2 negative, ammonium ion, and give amide ion. 2H2H3O positive plus OH negative. However, the extent of photoionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and ionic product. KNH3, NH4 positive, NH2 negative. KH2O, H3O positive, OH negative. 1 into 10 is to minus 14. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent. Liquid ammonia is a very poor conductor of electricity. The specific heat of ammonia is more than that of water. The liquid ammonia is less viscous than water. Most salt have, when dissolved in liquid ammonia, conduct electric current better than water. This is not due to the ionizing power of ammonia, which is about 1 by 3rd of water, but due to the low viscosity, which greatly increases the mobility of ions. Liquid ammonia has high critical temperature and pressure. It is less associated than water due to lesser hydrogen bonding, and therefore it is better solvent for organic compounds. Liquid ammonia forms strong reducing metal ammonia solution with alkali metals. Therefore, it is an excellent solvent for many reduction reactions. Reaction in liquid ammonia. Acid-base reaction. Liquid ammonia can be easily understood by comparing the reaction in water. 2H2O gives H3O positive plus OH negative. According to the solvent system concept of acid and base, the substance producing H3O positive ion in water act as acid, while those of producing OH negative ions act as base. Liquid ammonia ionizes 2NH3 gives NH4 positive plus NH2 negative. Therefore, the substance producing ammonium ions in liquid ammonia behave as acid, while those producing amide ions behave as base. For example, ammonium salts such as ammonium halide, thiocyanate, nitrate are soluble in liquid ammonia and behave as acid. NH4Cl gives NH4 positive plus Cl negative. Similarly, amide, imide, nitrite behave as bases in liquid NH3. The commonest base in the liquid ammonia is potassium amide, which ionizes as KNH2 gives K positive plus NH2 negative. Lithium amide, sodium amide, and alkaline earth metal amide have a very low solubility, and therefore KNH2 is commonest base in the liquid NH3. Protolysis. Certain compounds like urea, acetamide, sulfamide, which are incapable of donating proton to water, can readily donate protons to NH3 in liquid ammonia. These reactions are called protolysis reaction. However, these compounds act as acid in liquid ammonia. Sulfamic acid behaves as diabasic in liquid ammonia. Sulfamic acid behaving as diabasic in liquid ammonia. However, it behaves as a monobasic aqueous solution because NH2 group cannot donate a proton to water. Sulfamic acid behaving as monobasic in an aqueous solution. Acid-base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves a combination of H2O positive and OH negative to form practically unionized water. For example, neutralization of hydrochloric acid and sodium hydroxide may be represented as HCl plus NaOH gives NaCl plus H2O. In a similar way, the neutralization of an acid and a base in a liquid ammonia involves combination of NH4 positive ion and NH2 negative ion. NH4Cl plus KNH2 gives KCl plus 2NH3. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acid and bases are called amphoteric substances. For example, in liquid ammonia, the might show amphoteric behavior and analogous to that of zinc hydroxide in aqueous solution and a base. Thus, acids give NH4 positive ions and base give NH2 negative ion in liquid ammonia. These are termed as a monoacid and a monobases. Reaction of a monoacid. A monoacid is a substance that furnishes NH4 positive ion in liquid ammonia. Ammonium halide nitrate or thiocyanate are very soluble in liquid ammonia, giving NH4 positive ion, and their concentrated solution act as a monoacid. We know that acid give hydrogen with metals in aqueous solution. In a similar way, the monoacids react with alkali and other metals to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolve many oxide in similar way due to behavior in aqueous acid. Solutions of ammonium halides in liquid ammonia may be used as acid as the preparation of silane and arsine. Reaction of ammono bases. Ammono base is a substance in which a liquid ammonia solution gives NH2 negative ion. The commonest base is the potassium amide, which is much more than soluble than lithium and sodium amide. Metals that get monobases to give amide, imide, and nitrite, which get precipitated in liquid ammonia. Precipitation reaction involve double decomposition because the difference in the solubility of various substances in water and liquid ammonia. A large number of precipitation reactions, which are not normally possible in water, have been reported to occur in liquid ammonia. Silver chloride is precipitated in aqueous solution as KCl plus AgNO3 gives AgCl plus KNO3. Similarly, a white precipitate of BaCl2 is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. Iodides and bromides get precipitated when solution of various nitrates and ammonium halides in liquid ammonia are mixed together. Many metal sulfides can be precipitated in liquid ammonia by ammonium sulfide formed by the nitrate solution of metals. Ammonolysis. The soluble lysis reaction in the liquid ammonia called ammonolysis or ammonolytic reaction. These are analogous reactions to hydrolysis reaction and involve the attachment of ammonium ion to amide ion to the reactant. For example, hydrolysis of SiCl4 plus 4H2O gives salicylic acid. Similarly, ammonolysis of SiCl4 may be written as SiCl4 plus 8NH3 gives tetraamidosilane plus 4NH4 positive plus 4Cl negative. In excess of liquid ammonia, the ammonolysis of TiCl4 occurs in step TiCl4, TiCl3, NH2, liquid NH3, TiCl2, NH2, 2, liquid NH3, TiCl, NH2, 3, liquid NH3, Ti, NH2, 4. When organic halide which undergo slow ammonolysis are ammonolyzed at boiling point of liquid ammonia, a mixture of primary, secondary and tertiary amines are obtained. Rx plus 2NH3 gives RNH2NH4X, Rx plus R2NH plus NH3, R3N plus NH4X, where X is equal to Cl, Br, I or F. Though ammonia molecule is basic and has strong tendency to accept proton and therefore it will act as base. However, towards very strong base it acts as proton donor. Examples: NaH plus NH3, NaNH2, NaCH3 plus NH3, NaNH2 plus CH4, Na2O plus 2NH3 gives 2NaNH2 plus H2. Complex formation reaction. The many complex formation reactions in liquid ammonia are reported which are similar to reaction occurring in the aqueous system. For example, zinc nitrate react with potassium amide to form insoluble zinc amide, which is dissolved in the excess of amide due to the formation of complex compound of zinc. ZnNO3 2 plus 2KNH2 gives ZnNH3 whole by 2 plus 2KNO3, ZnNH2 whole by 2 plus 2KNH3, liquid NH3 K2 ZnNH2 4 soluble. This reaction is analogous to the reaction of zinc nitrate with sodium hydroxide in water. ZnNO3 2 plus 2 NaOH H2O, ZnOH2 plus 2 NaNO3, ZnOH2 plus 2 NaOH gives Na2 ZnOH4. Some other complex reaction in liquid ammonia are called CuCl2 plus 4NH3 gives CuNH3 4Cl2, AgCl plus 2NH3 gives AgNH3 2Cl, CrCl3 plus 6NH3, CrNH3 6Cl3. Formation of ammoniate. Just as water forms hydrates, ammonia also forms ammoniate with many inorganic salt. In these compounds, the ammonia molecules are coordinated to cation. Some typical ammoniate are BF3 plus NH3, BF3 dot NH3, MgI2 plus 6NH3, MgI2 dot 6NH3, SiF4 plus 2NH3, SiF4 2NH3, NiI2 6NH3, NiI2 dot 6 and redox reaction. Liquid ammonia act as an excellent medium for the redox reaction. Liquid ammonia, the oxidizing action of strong oxidizing agent is weaker than in water solution. For example, NH3 negative in liquid ammonia does not act as oxidizing agent. Similarly, KMNO4 in liquid ammonia act as a very weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metal act as very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduces CuI to Cu, KMnO4 to K2MnO4. CuI plus Na gives Cu plus NaI, KMnO4 plus K2MnO4. These form very interesting solution are discussed below. Non-metal like sulfur, phosphorus, iodine, as selenium are soluble in liquid ammonia. Solution of alkali metals in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. The resulting solution are blue and extremely good electrical conductors. The important characteristics of alkali metal solution are these are blue in color and color is independent of the metal dissolved, and the concentration of metal increased. The color changes to bronze and shows metallic appearance. These solutions are conducting and show strong reducing properties. These solutions are paramagnetic and paramagnetic character decrease with increasing concentration. If the reagent are pure and dry, the sodium solution is liquid ammonia stable and can be preserved for several days. When alkaline metals are dissolved in liquid ammonia, they ionize to give metal and valence electron. The complete reaction may be written as Na liquid NH3 Na positive NH3X positive plus ENH3Y negative. The ammoniated electrons are responsible for the blue color of the solution. This is due to the absorption of visible light by the ammoniated electrons. The electrical conductance is also due to the ammoniated cation electron. The conductivity of metal in liquid ammonia is comparable to that of an aqueous solution of a typical ionic compound. As the concentration of the solution is increased, the ammoniated cation and electron associated resulting in a decrease of conductivity. Very dilute solution of alkali metal in liquid ammonia are metastable, and when catalyzed they undergo decomposition. As the concentration of metal ion increases, the blue color changes to bronze and finally the blue color disc appears. This is due to the fact that impurities such as iron oxide catalyze the conversion of metal into white. Only evaporating the alkali metal ammonia solutions such as alkali metals can be recovered. The strongly reduced character of these solutions is due to the presence of readily available electrons. The important application of alkali metal solutions in organic chemistry is the reduction of many functional groups and unsaturated compounds. Advantage of liquid ammonia as a solvent. The dissolution of alkali metals without the chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metal can be recovered from the solution by evaporation. Alkali metal solutions are strong reducing agent and are even stronger than hydrogen. Ammonium salts dissolved in liquid ammonia act as a mono acid, and these find application in preparative chemistry. They can be used to prepare silane, acetylene, etc. The tendency for soluble acids is less in liquid ammonia than in water. Disadvantage of liquid ammonia as a solvent. The liquid range for liquid ammonia is from -33.3 to 77 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Liquid ammonia has an offensive odor, therefore it requires special techniques to use it as a solvent and a reaction medium. Liquid ammonia is hygroscopic in nature, hence all reaction will be carried out in sealed tube. Liquid sulfur dioxide is a non-protoning solvent, a protic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvent and has been widely used in the industry. Under normal condition of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefy and easily maintained in the liquid phase. It has a wide liquid range -10 to -75.5 and can be used as a solvent. It can be easily purified by passing a gas to sulfuric acid and through P2F5 to remove traces of water. The electric constant is small, therefore is a good solvent for covalent compound. Structure of sulfur dioxide molecule. Electron obtaination study shown that sulfur dioxide in gaseous phase an angular structure as shown. The valence bond therapeutic data SO2 molecules resonance hybrid flowing to resonating structure. Solubilities of compound in liquid in sulfur dioxide. Among the inorganic compound, iodide and thiocyanate are most soluble. In case of alkali metal halide, the solubilities are in the order Mi, MBr, MCl, MF. The uni-negative polyatomic anions such as ClO4 negative, NO3 negative, BF4 negative are generally more soluble in the liquid Sp2. Sides of negative anions such as SO4 negative, SO3 negative, S2 negative, O2 negative are practically insoluble. Many of the ammonium, thallium, and mercuric salts are soluble. It is an excellent solvent for the covalent compound. Many covalent substances like halogen, interhalogen, phosphorus halide, oxyhalide of sulfur, phosphorus halide are soluble in metal are insoluble. Among the organic compounds, aromatic hydrocarbon and gills, pi-bonded compounds have very high solubility in liquid acetate comparison to saturated hydrocarbons, pyridine, quinol, ether, halogen derivative, and acid chloride are also dissolved in SO2. Many compounds dissolved in SO2 due to solvent formation. For example, Kl Ca2, 4s2, KCnSO2. Many donor molecules also form stable solvent. C5H5nSO2, C6H5, SO3, BF3, SO2, etc. Auto ionization. Poor SO2 is a poor conductor of electricity, though it is believed to autonize as a 2SO2 to SO2 positive plus SO3 negative. Ethynyl ion is analogous to hydronium ion and ammonium ion and sulfite ion, corresponding to hydraulic ceramide ions of the aqueous ammonia system respectively. Reactions in liquid sulfur dioxide, acid-base reaction. Liquid SO2 undergoes ionization. 2SO2 gives SO2 positive, SO3 negative. According to the solvent, the concept of acid and base, the compounds which give thionyl ions in the solution of SO2 would behave as acid, whereas compounds giving sulfide ions in liquid would act as bases. For example, compounds such as SOCl2, SOBr2, etc. act in liquid SO2. SOBr2 gives SO2 positive plus 2Br negative. On the other hand, cesium sulfide increase the concentration of sulfite ions and therefore CS2SO3 base is 2CS2 positive, SO3 negative. Typical acid-base neutralization reaction in liquid SO2 may be given as SOCl2 plus CS2SO3 gives CSCl plus 2SO2. SOSCN2 plus K2SO3 gives 2KSCN2SO2. Amphoteric behavior is shown by zinc and aluminium. For example, AlCl3 with SO3 negative ions in the liquid SO2 to form insoluble aluminum sulfate. However, if the precipitate is treated with excess of sulfide, the precipitate redissolves. This reaction is analogous to the behavior of AlH3 in water. If some acid is added to the soluble complex solution, the aluminum sulfate precipitate. Solvolytic reactions. Solvolytic reactions in liquid sulfur dioxide are not as common as they are in protonic solvents such as NH3. Some reactions are given below. Ammonium acetate is solubilized to liquid SO2. This reaction is analogous to reaction of ammonium acetate in water. Certain solvent halides such as PCl5, PBr5, UCl6, AsCl5, WC undergo solubilisis in SO2 sealed tubes. PCl5 plus SO2 gives POCl3 plus SOCl2. PBr5 plus SO2 gives POBr3 plus SOBr2. UCl6 plus 2SO2 gives UO2Cl2 plus 2SOCl2. Like this, many halides such as SbCl3, SbCl5, SiCl4, SnCl4, VCl3, SCl2, etc. do not undergo solubilization in liquid sulfur dioxide. The formation of solvates in the addition compound with a solvent is unknown. Typical example of solvent are NaI.4SO2, KBr.4S2, CI2.4S2, SRI2.4S2, AlCl3.2SO2. Precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to the selective solubility of compound. The precipitation of several insoluble compounds in liquid sulfur dioxide can be carried out by treating the soluble compounds in sulfur dioxide SbCl3 plus 3 LiI, SbI3 plus 3 LiCF, AlCl3 plus 3 NaI, 3 NaCl plus AlI3. Thionyl derivatives can be easily prepared in liquid SO2 by the action of thionyl chloride. 2Ki plus SOCl2, 2KCl plus SOI. Complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium rubidium iodide. This is due to the formation of complex Ki3 or RbI3. Ki plus I2 gives Ki3, RbI plus I2 gives RbI3. Similarly, the increase in the solubility of cadmium iodide and mercuric iodide in liquid sulfur is attributed to the formation of complexes CdI2 plus 2Ki, K2CdI4. AlCl3 reacts with SO3 2 negative ions to form a precipitate of Al2SO4 which redissolves in excess of SO3 2 negative, forming AlSO3 3 negative. Organic reaction. The large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is a relatively inert solvent. Sulfonation by aromatic hydrocarbon by sulfur trioxide or chlorosulfuric acid gives C6H6 plus SO3 C6H5SO3H. Liquid SO2 has been used as solvent for fetal craft type reaction. In this reaction, C6H6 plus TC3 C5H11Cl liquid SO2 gives C5H11C6H5 plus HCl. It is also used as solvent in addition for the substitution of bromine reactions. Styrene plus Br2 gives benzene CHCH2Br, phenol plus Br2, phenol OH Br plus HBr. Sulfur dioxide of crystallization. These reactions are also called sulfation reaction, like water ammonia salts having sulfur dioxide of crystallization have also been observed. Some examples are NaI4S2, Ki.4S2, LaI4S2, Bi2,4S2, Al3SO2. These are formed with highly soluble salts. Redox reaction. These two gases, sulfur dioxide, behave both as oxidizing and reducing agent. Liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as medium for the certain redox reaction. For example, iodine is liberated from the Ki in the presence of SbCl5 in liquid sulfur dioxide. 6Ki plus 3SbCl5 gives 2K3SbCl6 plus SbCl3 plus 3I2. Some special feature of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantage over the other solvent on the reaction with the medium. It has low boiling point and this allows its easy evaporation, therefore removal from the reaction mixture. It has low melting point and therefore it allows to be carried out to low temperature. Liquid SO2 is inert solvent. It has unusual solvating power for both electrovalent compound. It is better medium for covalent compound like hydrocarbon and is used for the purification of some petroleum product. It is used for diluent for the superacid medium HSO3F SBF5, which helps in reducing its viscosity without affecting its acidity. Thank you.